This is part 2 of the video, and we're going to maybe add one more uh, probe. So this is the joint that turns the crank, and if we ask for some results, and not force but moment, this is how much torque it takes to drive that gear against the 20 Newton load. And let us evaluate all results, and we can turn off the moments we don't care about, and it's really the total moment that we are interested in, and that's really the same as the Z moment. So the moment goes from 600 up to 680 as the 20 degrees is rotating against that 20 Newton load here. So in this configuration, 682 Newton millimeters of torque to push against that 20 Newton load. All right, we are going to now take the model in this configuration as opposed to the starting configuration into static structural and change some of these rigid bodies into flexible bodies. So the way we do that is we grab a static structural, add it to the model, and then take the solution cell and drop it on the model cell. And that will, after we update this and open this new model, allow us to do some edits there. And we'll wait for mechanical to start. So mechanical has started, and if we take a look back at the workbench, on the solution tab, you can see that we're sending over the configuration at the end time. But if we wanted a different angle than the end time, we could use a user-defined time to send into this new model. But the end time is what I wanted, and that's what we've got. And now we can use the parts in this orientation to do some stress analysis, and this we'll be able to apply forces as measured over there. So I can do this in 3 separate analyses, which makes things very simple, and take just the can suppress the crank and suppress the finger, which is this one. Suppress that body and just mesh and apply loads to this. So that's what we'll do here, and that one body is going to be flexible instead of rigid, so that's an edit we need to do. Under the mesh, we may want like a millimeter default size, and if we add some mesh controls, we can improve on the default mesh. All right, we're going to improve the mesh a little bit by inserting a method on the body, and that method is sweep. So we're going to sweep. We're going to sweep from a front face, which would be this front face here, and that face will sweep out 4 elements through the thickness. Then we can also pick that face for another method called inflation. In other words, inflate the sweep using a boundary of this and control that. And we want, say, 3 elements, maybe over a total thickness of, say, 2 millimeters. And we also may want to insert some sizing on these two edges. Maybe not size, but number of divisions, 20. And now let's see how that looks. So that's pretty nice. We only got 2 elements around there, but that's not bad. And I think we'll take that mesh. Now we need some boundary conditions. And the boundary conditions, there is a support called compression only. And compression only is excellent to represent a pin pushing on the side of a hole. So the face here would be this face, and that allows no, if it's under compression, all the load will go into this side and none of it will go into that side. And then a similar condition on the other end of the body is called a bearing load on this face, and the bearing load will be the 104 newtons that was measured by, and that is along a direction that is straight along here. So bearing load will put all of those newtons on this side of the hole and none of it on that with a cosine fall off. So that's a very accurate way to represent what's going on. Okay, the last thing we need is a constraint to prevent this from rotating away, because all we've got is a force. So we're going to need a coordinate system that is aligned with this. And so we will first go up to coordinate systems and insert a new coordinate system. And we'll put the origin at the center of the body. And there it is. But down here, let's put the principal axis of Y and make it not global, but a geometry selection of this face. And so now the y-axis is up and the x-axis is correctly aligned. So we can select, say, this face here as a new support, which will be a remote displacement using the newly created coordinate system, so that we can leave x free and make y 0 so it can't spin around this pin, and z, it can't fall off the pin. But it's a deformable behavior, so it's not going to interfere with the stress around that part in any way. So with all those and the good mesh, we are set to solve, and when we solve, we'll want to look at directional deformation, maybe along the new coordinate system, and the x-axis will be the compression, and insert some stress and maybe some max principal stress, min principal stress. So we'll solve that and see what we get. And here is our compression, a minus small number of millimeters. The material, I believe, was structural steel. We'd get a little more. Okay, let's see the results. The stress is about 8 megapascals, and as we expect, concentrated where the compression load is coming in, and a little bit near the bend lines. So fairly uniform pressure in the middle, and the max tension is in the sides of the holes, but most of the load is in the compression, and since the compression stresses are negative, it might be good to change this to a color scheme reverse rainbow. So the high compressive stress is where we expect it to be. And so that is a brief illustration of the workflow to do one, and I'll stop this recording and maybe make one for one of the other objects, but it's the same workflow. So hope you enjoyed that. Thanks. Bye.